Okay, so it's now time for our last talk of the day. So Marcus Spradlin is going to tell us about amplitudes and polytopes.
Thank you. Can you confirm that you can hear me, please?
You're good.
Okay, excellent. Yeah, thanks. It's really an honor to give this talk. I'm happy to extend the boundaries of my connectivity graph, even if it's defined only by knowing people and not yet by collaboration. Since Young encouraged me to give I'm not sure I lived up to Young's encouragement to give a colloquium level talk. At least the first half of it, I hope, will be somewhat toned down. There are a couple of technical slides near the end, but hopefully if I'm running over time, I can just fluster my way through them and then spare you the pain. So, and also Anastasia's talk that just preceded mine does a good job of motivating the overall problem that we're interested in. So that lets me start at a slightly more advanced position. But the work that I'll be talking about today will be mostly based on a couple of papers written with Nima Arkhani Hamed, Thomas Lamb, our student Li Cheng Ren, and Anastasia. So again, you've already heard this. In recent years, we've seen remarkable progress on the problem of unlocking the mathematical structure of quantum field theory. And I'm jumping right in. As introduced by Anastasia, the focus of my talk will be the planar n=4 supersymmetric Yang-Mills theory, which we call SYM theory for short. And for mathematicians in the audience, I like to encourage mathematicians to think of SYM theory like an oracle. Okay, consider the physicists like oracles who hand you these encyclopedias filled with functions that have really remarkable properties and interrelationships. And in fact, there's a sense, because super Yang-Mills theory is in a fairly particular, fairly precise sense, a unique quantum field theory, there's a sense in which these functions and their interconnected web of interrelationships barely exist. It's like a tower of cards whose structure is so constraining that if you tried to tweak one little bit here or there, the whole thing would collapse. So because of that, some of us are interested in the question of whether one can formulate a purely mathematical set of criteria or properties that uniquely identifies or uniquely determines this entire stack of cards. So the first question you should ask yourself, if you want me to convince you that this is an interesting collection of functions, is you should ask, well, what are they functions of? So a primary motivation for my talk will be to really try to understand what is the natural kinematic domain for these amplitudes. What are they functions of? And secondarily, or consequently, to see if there's any imprint of the mathematical structure on the amplitudes themselves. And it'll become more clear what I mean, hopefully, by these questions. So, okay, let's just start with the basic question: what are scattering amplitudes functions of? Well, a physicist would say that if you're scattering n particles, the scattering amplitude will be a function of, let's say, the energies and the momenta of those particles. And we call these kinematic variables. So therefore, we call the space on which these variables live the kinematic domain. Now, we can just do some simple counting here. If you have n massless particles, well, each one is traveling at the speed of light in some direction. So you need a vector in R3 to specify the direction it's traveling. So you need 3n variables. But then there are some symmetries which constrain the problem. First of all, you have the isometry group of Minkowski space. That is the space of translations, rotations, and boosts that comprise the Lorentz and Poincaré groups. So that's a 10-dimensional space. So then the effective number of degrees of freedom is reduced by 10. But then, in addition to that, super Yang-Mills theory has a really non-trivial symmetry almost unique in four-dimensional quantum field theories. It has a special symmetry called dual conformal symmetry, which accounts for another a loss of another 5 degrees of freedom. So altogether, the dimensionality of the kinematic space on which these amplitudes live is 3n minus 15 dimensional. So right away at the end of Anastasia's talk, there was a question about 4 and 5 particle amplitudes. And indeed, once you factor in the dual conformal symmetry, these are essentially trivial. For example, even if you plug in n equals 5 here, you get a 0-dimensional space telling you that there's no room for non-trivial functional dependence on any of these kinematic variables if you have less than 6 particles. Okay, now, although physicists think about these variables in terms of energy and momentum, it's better to expose the mathematical structure. It's better to use a different parametrization of this space. I'm not going to explain how these are related to energy and momentum, but I'll just recall Anastasia already gave the basic definition of this. We use variables called momentum twisters, which work as following. You take just n arbitrary points in P3, have each one of them represented by a 4-component homogeneous coordinate, put them in the columns of this 4 by n matrix that I call Z, okay? And in this representation, dual conformal symmetry just acts by left multiplication by an arbitrary invertible 4 by 4 matrix. So altogether, the kinematic space is, well, you can think about it either as a quotient of the Grassmannian or as a quotient of this matrix modulo PGL4. I'm sorry, I said the same thing twice. What I meant is it's an element of the Grassmannian, but keeping in mind that you're allowed to rescale independently each of the n columns by an arbitrary non-zero complex number, because after all, each column is a homogeneous coordinate on P3. So altogether, the space, we use the notation conf 4 comma n, which means configurations of n points in P3. Now, the fact that this space has the structure of a cluster Poisson variety apparently underlies many of the connections between amplitudes and SYM theory. And Anastasia talked a little bit about that. And my talk will focus on ways in which these amplitudes sort of extend beyond the cluster realm. Okay. Now, amplitudes are multi-valued functions. Oh, and so in physics, of course, energy and momenta are always real. But of course, if you're studying functions, it is often useful to allow yourself the freedom to consider your kinematic variables to be arbitrary complex numbers, so you can use the whole powerful machinery of complex analysis. So for the moment, it's convenient to allow ourselves to complexify this space. And on that space, amplitudes are multi-valued functions. They have poles. The poles are completely well understood. So the singularities that are of interest to us are branch points. And because these are multi-valued functions, they need to be defined by analytic continuation, starting with some initial definition where initial domain, you need to start with an initial domain, kind of like when you write down a power series and you say, okay, here's a power series, it converges in such and such domain, and then I define it by analytic continuation elsewhere. Now, a very special role is played by what we call the positive Grassmannian. And this is a famous in mathematics. It's associated to a lot of beautiful structure. It's the open subspace of the real Grassmannian cut out by the condition that all the ordered Plücker coordinates should be positive value. Okay. And the positive configuration space is the image of the positive Grassmannian under this quotient. Let me go back 2 slides. Here I've got a quotient of the Grassmannian by C star to the power n minus 1, because you can rescale independently all of the n columns. It's only n minus 1 instead of n, because if you were to rescale all the columns by the same amount, that wouldn't change the representative that you have in GR4 comma n. So, but anyway, but when I write here on this slide, oops, yeah. So sometimes you'll see the terminology simply I should have written it on this slide. I regret that I didn't. You'll see GR4 comma n mod capital T, where capital T stands for that torus, C star to the n minus 1. Okay, so I just wanted to clarify that if it comes up later. Okay, now, a central conjecture in our field, and there's some evidence to support this, it's quite well understood for low n, less well understood for high n, is that amplitudes are non-singular everywhere inside of this positive domain. However, it's indeed precisely the boundaries of this domain that we're especially interested in. I had a slide for the physicists that I deleted, but it's a dream of going back to Heisenberg, that one should be able to determine scattering amplitudes purely by a thorough understanding of their analytic structure. So in this context here, if you want to have a thorough understanding of their analytic structure, it's precisely the boundaries of this positive domain that we want to understand very well, because that's where the singularities of these amplitudes lie. And this is tantamount to identifying a suitable closure or compactification of this space conv 4 comma n plus, which is an open set, in fact, homeomorphic to a ball. And moreover, taking a cue from some areas in physics where similar problem arises, namely in the open string moduli space that I'll say a tiny bit about later, we are motivated to seek polytopal realizations of these compactifications, which manifest all of the boundary structure. Now, in case some of these words are a little abstract, now let's do an example in great detail so that I hopefully clarify what I mean. Let's look at 6-particle scattering. And here are some conformal cross ratios you can define. You've already seen these in Anastasia's talk. These are just ratios of Plücker coordinates on the Grassmannian GR4 comma 6. And this is a common basis of cross ratios that's used in the literature. Now, in terms of these, the positive configuration space is the part of the unit hypercube satisfying this rather strange looking inequality here. If we graph it, so here I've shown the unit hypercube in U1, comma U2, comma U3 space. On the left is the origin, and you see there's this kind of pillow-shaped region near the origin, and the interior of that is really the positive domain. Okay, and so the question we want to know is, does this picture accurately portray the boundary structure of the closure? And of course, the answer is no. That's going to be the subject of the next 2 slides. But let me illustrate this by a simpler example. And I'm going to go a little quickly here because this is a little embarrassing to give to mathematicians, because all I'm going to be doing is explaining what a blowup is. So let's consider a toy model of a 2-dimensional kinematic space parametrized by 2 variables that take values in the interior of a unit square. And let's ask the question, is a corner of that square, 1, comma 1, really just a point? Or is it more than a point? And the answer is it depends on what the natural functions that we're interested in studying on this space are. So for example, if the universe of functions that we're interested in studying are polynomials in x and y, then yes, 1, comma 1 is really just a point. There's no additional structure there. But if the universe of functions that we're interested in studying contain things like the following, and here I've written some examples of more complicated rational functions on x and y, then you can observe that if you approach the point 1, 1 along a path that I've indicated here, path, oops, why am I using t and epsilon? That's rather embarrassing. The t should be epsilon. So I apologize for that. So you're taking epsilon to 0 along the path parametrized by the equation in the middle, where alpha and beta are arbitrary positive constants. And if you shove this into the definition of the u variables at the top of the page, and then take the limit, you'll find that 2 of the u variables approach values that depend on your choice of alpha and beta. So in other words, that what you thought was a point 1, 1 actually looks different depending on what angle you approach that point from. So this makes it manifest that 1, 1 is not a single point, but a line segment parametrized by the value of either u3 or u5 as alpha and beta range over all positive numbers. Okay, so in this case, using the u variables, the interior of the unit square actually maps to the interior of a pentagon, and each edge of the pentagon is labeled by the u variable that vanishes on that edge of the pentagon. For example, in this here, the edge that you get at the blowup of 1, 1, I would call it the edge where u4 vanishes. Okay, now this was, you might have thought this was a contrived example, but string theorists know very well that this is anything but a contrived example. This is basically an example of the open string moduli space for n equals 5. So if you consider a matrix of this form, and you demand that this matrix be positive in the sense that the ordered Plücker coordinates should take positive values, then that is satisfied as long as x and y satisfy the inequality given on the bottom line. So this corresponds to a configuration of 5 points in P1 modulo the action of SL2 from the left. So, and the u variables that I used before actually are just simple cross ratios of the Plücker coordinates written here. Okay, so this example was nothing more than the familiar Deligne-Mumford compactification of what physicists would call the open string moduli space, or what in the language of today's talk, I'll call the compactification of GR2, 5 mod torus. Okay, now if we go back to 6 points, if you do an appropriately analogous exercise for the 6-point kinematic space, it maps this into a well-known surface called the K5 associahedron. I'm cheating a little bit here because to go from the left to the right, you're also going to a double cover of the space. So, but let me skip that detail. So here on the right, you've blown up all of the boundary segments that are hiding. So the points at the tip of the left are not really points, and the line segments are not all line segments. Some of them blow up into surfaces, and the right is what you get after you do this appropriate blow up. Okay. Anyway, moving back to Super-Yang-Mills theory, as I emphasized in my example, in order to know what is the right blow up that you should be looking at, you need to know, or it's dictated to you by the class of functions under consideration. Now, for us, we're interested to know what is the appropriate blow up of the kinematic space of Super-Yang-Mills theory. So, in principle, the answer to that question should be dictated to us by the amplitudes themselves. Now, we kind of want to go the other way. We want to see if we can construct a guess, use some mathematically natural construction to generate various mathematically natural blowups, and then see if any of them, strike a chord. Do any of them exhibit some structure that seems to be compatible with the structure that we see in amplitudes? So we're kind of trying to reverse engineer this problem. Now, in general, the problem of understanding compactification of GRK comma n mod torus is much more challenging than that of 2 comma n, because you can have much more intricate sets of codimension 1 type configurations. So in GR2 comma n, the only type of codimension 1 configuration is when 2 points in P1 collide. So all of your codimension 1 boundaries have that type. But in GRK comma n with k greater than 2, you can have more intricate kinds of codimension 1 boundaries. You can either have 2 points colliding, or, for example, in GR3 comma n, you can have 3 adjacent points becoming collinear. And that's also a codimension 1 facet, if you will, of the polytope we're trying to construct. And you can have much more complicated configurations as you go to higher k. So actually here, I think I restated the question from the previous slide. Which, if any, compactification of this configuration space actually underlies the structure of amplitudes? And instead of reading off the answer, because we don't have all the amplitudes at our hand, they're difficult to compute, we'd rather guess some polytope and then see if we can use that guess to tell us something about amplitudes, maybe help push some new calculations out the door that are otherwise very hard to do. So in the paper with Nima and Thomas Lamb, we explored candidates that are naturally constructed using stringy canonical forms. And these are dual to certain fans that were studied several years ago by Spire and Williams, associated to the positive tropical Grassmannian. So let me just very briefly explain the construction of these polytopes. First, you consider what we call a cluster parametrization of the interior of this positive configuration space. These can easily be generated using the beautiful work of Postnikov, who used Playbit graphs. So there's a mechanism to read off from a given Playbit graph a parametrization of the top cell of the Grassmannian. And then what we're going to do is for each Plücker coordinate P, you evaluate it on that parameterization, and you let Newt of P be the Newton polytope in RD with respect to that parameterization. And 2 talks ago, we also heard about the application of Newton polytopes in another guise in physics. So it's kind of cool that everything's coming together. And then we define the polytope we called C dagger as the Minkowski sum of all of the Newton polytopes for a very special class of Plücker coordinates. Now, let me just comment very briefly on this. If you have some choice here in how to define your polytope. If you use all Plücker coordinates, that would give you the dual of the Spire-Williams span. We found that a smaller polytope seems sufficient to be able to describe certain features of 6, 7, and 8, and 9 particle amplitudes. So we basically want to see what's the smallest polytope we can get away with for now. And if we need a larger, more intricate one, we'll turn to that in the future. But a good candidate seems to be one that's slightly smaller or more coarse than the Spire-Williams polytope. And it only involves taking the Plücker coordinates of the form that I've written here. Now, when you do that, you can compute all the combinatorial data of these polytopes. for various values of n. Here I've drawn the f vectors. So these are the vectors that tell you the number of faces of various dimension. The first one here, 14, 21, 9, we've already seen that here. This polytope here has 14 vertices, 21 edges, and 9 faces. Okay, you can do a similar construction for 4, 7, 4, 8, and also now 4, 9 in later work. But really the relevant point is the following, that by virtue of choosing a cluster parametrization, that ties the geometry of this polytope to that of the associated Grassmannian cluster algebra. And in particular, in the finite cases that, where the cluster algebra is finite, the normal rays to the facets of the polytope correspond to cluster variables. They're things that in the cluster algebra community are called G-vectors of the cluster algebra. So the point is that there's a very natural way, at least in the finite cases, to take one of these polytopes and assign a cluster variable to each facet. And the set of cluster variables you get is exactly the symbol alphabet of the 6 and 7 point amplitudes that you heard about in Anastasia's talk. Now, the thing that's precisely of interest to us is what happens starting in GR4, 8, where two things happen. First of all, the cluster algebra is no longer finite. And second of all, we know that in the amplitude data, you start seeing algebraic functions of Plücker coordinates that are certainly not cluster variables. So there's a really interesting story here, which is that, let's start with the case of GR4, 8. When we do this construction, here we find a polytope with 274 facets. We find that only 272 of the normal rays, right? There's a normal ray to each facet. Only 272 of them correspond to cluster variables. The other two, in the language of cluster algebras that I'm not reviewing here, the other two lie outside the cluster fan. And so here's one of them. I mean, without explaining our conventions and everything, it makes the numbers here have no meaning to you, but just to show that there was some calculation done here. Now we used, in order to check, to convince ourselves that this is not actually a cluster variable, let me repeat. In GR4, 8, there are infinitely many cluster variables. So if I asked you, is there a cluster variable whose G vector is this vector shown here, you know, you could try mutating and mutating until the cows come home, and you would never prove me wrong. You might just be unable to find it. But we used a criterion from a recent paper by Chang et al. That lets you do a particular calculation. You're basically calculating a certain character or invariant associated to these vectors, and you can check whether or not something is a cluster variable. And in fact, this vector appears in their paper as one of their examples. So that was really exciting. Using the character formula in that paper, you can in principle compute what's called a cluster algebra basis element along each integer point along the ray. So you have the polytope. We have two special facets that are not associated with cluster variables. Each of those facets has a normal ray. You can look at the sequence of integer points along that normal ray. You can use the character formula to calculate a quantity associated to each of those integer points. Here I've written the first three of them. And then you could imagine writing down a generating function that contains all of the information along that ray. Now, we only calculated the first 3 points, using the CDFL character formula, the calculations are extremely difficult. They have computational complexity of order 4s factorial, but based on these 3 data points, we made a conjecture that you get a simple generating function like this with the quadratic function of t in the denominator. Okay, those were my 2 or 3 technical slides. So now let me bring it back down to earth a little bit. We have a mechanism for constructing these polytopal compactifications of the kinematic domain. Then we have a natural mechanism to associate to some facets of the polytope cluster variables, and to other facets of the polytope, these kind of quantities that somehow go slightly beyond the cluster algebra universe. Well, they're not cluster variables, they're closely related to cluster variables. But the point is the following: we observe that if you look at the denominator of this quadratic generating function, it has square roots of this form. It has roots of this form. And these are precisely, on the nose. These are the algebraic symbol letters that appear in, let's say, the two loop 8-point n squared MHV amplitude for the experts in the audience. But more generally, these square roots are exactly the type that appear in the algebraic symbol letters of scattering amplitudes. So altogether, this is a construction that accidentally reduces to the usual cluster algebra case for n equals 6 and 7. But for n greater than 7, extends beyond that and gives you something that gives you some cluster variables and some algebraic functions of cluster variables, exactly what we see in amplitudes. So this provides some evidence supporting the idea that these polytopes, at least combinatorially, might have some direct connection to amplitudes. Now, in subsequent work by Drummond et al., they have a more refined algorithm which really reproduces all of the 18, I don't have time to go into too many details here, but they reproduce all of the 18 algebraic symbol letters that appear in 8-particle amplitudes. Okay, now I am running somewhat low on time. So this concludes one line of attack that we've had. And briefly, in a couple of minutes, I want to talk about another line of attack that we've used more recently in this paper with Li Cheng Ren and Anastasia. We brought to bear, so we introduced to the physics community, or brought to bear, a new mathematical tool to this problem. And that tool goes by the name of tensor diagrams and the Fomin-Kolovsky conjectures. So a tensor diagram, and it's really remarkable because tensor diagrams to an untrained eye look remarkably similar to Playbit graphs, although there are some differences. I have some examples on the next slide. Here are 3 of them. An endpoint tensor diagram for SLK is a finite graph drawn in a circle with n marked points on the boundary, all boundary vertices colored black. Interior vertices can be black or white, but importantly, each edge has to connect a black and a white vertex. So those are the rules here. And now to each tensor diagram, you can associate an invariant in the following way. First of all, to each of these external points, 1, 2, 3, 4, 5, 6 in this example, you associate a momentum twister, a homogeneous coordinate in pk minus 1, a homogeneous coordinate of a point in pk minus 1. Then to every white vertex, you associate, now I'm switching to physics speak, basically an epsilon symbol with upstairs indices, to every black vertex, an epsilon symbol with downstairs indices, and then you contract the indices according to the edges in the diagram. And so this computes for you an invariant associated to each diagram. And there are 3 examples listed here using some notation that's more or less obvious in this case, but you saw similar types of expressions in Anastasia's talk when she was enumerating symbol letters. Now there's an important detail here that when k is even, these rules do not fix the overall sign of the invariant, and there's an important detail there, but let me skip that for the moment. As their name implies, tensor invariants are invariant under graphical moves called the Skine relations. Here are some examples of Skine relations for SL3 on the left and SL4 on the right. A web is a planar tensor diagram, and an arborizable web is a web that can be turned into a tree diagram using Skine relations. Okay. Now, importantly, that tree diagram need not be planar. So you have to start with a planar diagram that's not tree. And if you're able to use Skine relations to turn it into a tree diagram that's non-planar, possibly non-planar, then it's arborizable. So the main Fomin-Pilavsky conjecture for our application is that the set of cluster variables for the GKN algebra is equal to the set of indecomposable arborizable web invariants. Now, I'm skipping here sort of the main point of our construction, which occupies the bulk of the paper, but we have an algorithm for assigning a tensor diagram to each facet of our polytope. And the tensor diagrams that are webs are arborizable, those correspond to cluster variables in the same sense that I've already described previously. So what we did in the latest paper was to look at what we called almost arborizable web diagrams. Those are ones that you can't get rid of all of the loops, but you can sort of reduce them to one loop, okay? So they're not quite arborizable, but they're almost arborizable. And for every such web, we assign a formal power series. So this is supposed to be very reminiscent of the power series I had a few moments ago. The power series, the first non-trivial term in the power series is the web invariant associated to W. And to get the higher terms in the power series, there's a very simple operation. You take M copies of the web, one on top of each other, or like draw them all together inside the same circle, basically on top, almost on top of each other. Then you take the M inner loops. So you have M non-interacting inner loops. They're not touching each other, but you do a simple permutation where you cut each one, you connect loop number 1 to loop number 2, loop number 2 to loop number 3, etc., so that the M distinct loops turn into one giant loop of length M, or M times the original length. So that gives you a new diagram that has one loop in it, and you can compute its invariant, and that gives you WM. Now, the nice thing about this construction is that we were able to prove, using the Skine relations, we were able to prove recursively that the power series associated to such a web, you can write an exact expression for, and here it is. 1 minus bt squared over 1 minus at plus bt squared, where a and b are exactly the same a and b that appear in this power series. Now, these two power series, this one here and the one with 1 minus bt squared in the numerator, they're very closely related. It's like the difference between, I'm getting a Chebyshev T and U polynomial. It's very, very closely related to each other. But the crucial point is that we're able to prove this to all orders. And so this extends the construction we had with Arcani, Ahmed et al., and better establishes the connection to algebraic symbol letters. So we were able to do this for G48, and G4-9, at least for almost all. We weren't quite able to do all of G4-9 because there were some facets associated to webs that are not almost arborizable. They have more than one loop, and we don't yet know what to do with those. Those could be a sign that you're going to get symbol letters that have higher order denominators, maybe cubic denominators. We just don't know. But anyway, I've reached the end of my scheduled time, so that's good. And I'll leave some time for questions, hopefully. But to summarize my talk, I've described some natural polytopal compactifications of the kinematic domain of n-particle amplitudes in super-Yang-Mills theory. The combinatorial and algebraic structure of these polytopes is imprinted on the structure of the amplitudes in a highly non-trivial ways, for example, by apparently describing their symbol alphabets. So all of those, the long lists of symbol letters for 8 and 9 particles that you saw in Anastasia's talk, those are all included in the lists of cluster variables that we get associated to these polytopes. They just pop out. Notably, we see other cluster variables that haven't appeared yet in physics calculations, possibly because we're looking at the wrong polytopes, or possibly because those additional symbol letters appear in higher loop calculations that have not yet been performed. So finally, to end with some to-do list, we should better understand the choice of compactification, like which is precisely the correct compactification to use for n=4 super-Yang-Mills theory, and how do we harness this knowledge to learn more about amplitudes. Or, you know, a big goal in this game is to guess some mathematical structure, use that guess to compute some new amplitude, which is otherwise impossibly difficult to compute, and then cross-check that calculation against other known results to see if you're on the right track, or if you can further corroborate some mathematical structure. Okay, I'll end here. Thanks so much for your attention.
So let's give Marcus a hand. And questions.
Can I ask about this polytopal part? So in the beginning, you have this Newton polytopes that correspond to a very specific set of cluster variables, right? But you also said that you start with initial cluster. So what changes if you, well, so is there a more convenient cluster to start with, or you pick one at random? How does it work?
Yeah, we start with the initial cluster. It shouldn't matter. Okay. I don't think it matters. Yeah. Yeah.
As
long as it's consistent.
Yeah, because some of them can be in the initial cluster, and then your Newton polytope is
right. Yeah.
Okay, thank you.
I have a question, Mark. Hi, this is George. Very nice talk. So just a very simple question that I always get confused about. If I think about this kinematical domain, right, I can even think of a non-interacting theory. Can I? Let's say, for example, I take just a free theory, right, or asymptotically free if you want something non-trivial.
Sure.
So how do I think then about that case, which seems to be trivial from the point, well, free theory, trivial from the point of view of the amplitudes?
Well, maybe I don't quite understand the question. In a free theory, the amplitudes would be 0.
Exactly. So how do I think, but in asymptotically free theory, they would not.
Right. Oh, yeah.
So how do I think about that kind of this is, if you think in terms of Lagrangian and so forth, we kind of start from the free side, perturb, blah, 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 and they introduce interactions. Here, there is a much more general kind of S matrix type of picture, right? And so how do I understand the trivial, if you want, the free limit, or even something non-trivial like asymptotically free case.
Yeah, because I don't know the answer to that question, I'm going to answer a different question.
Okay.
Yeah. So so obviously n equals Fourier-Mills theory is very different
Of course.
from two things I can say. A program like the one that, this could all be pie in the sky, but a program along the lines of what I'm describing here probably would be hopeless in a theory like QCD. So two reasons why it might not be hopeless in n equals Fourier-Mills theory are, first of all, that the theory has so one of the things I didn't emphasize but should have emphasized is that the polytopes we're looking at are labeled only by n, the particle number. They're not labeled by loop order intentionally, because the pipe dream is that for every n, there's a single polytope that governs the structure to arbitrary orders in perturbation theory. And maybe even non-perturbatively, but who knows, at least to every finite order in perturbation theory. And you know that planar super-Yang-Mills theory has a finite radius of convergence.
Mm-hmm.
So that's a nice piece of evidence, or well, not evidence is too strong a word. A reason why it might not be guaranteed to fail. Another thing is that in a paper 3 years ago, we showed that in a massless planar theory, like n equals Fourier-Mills theory, it is true that for every n, there's the locus in kinematic space on which amplitudes can have singularities is finitely generated, even at arbitrary finite order in perturbation theory. So that is something which you wouldn't expect to be true in QCD, for example. So that bolsters the hope that in the theory like n equals Fourier-Mills theory, there is some polytope that has some meaning regardless of loop order, and maybe even non-perturbatively. So I know I didn't exactly answer your question, but I gave some reasons why I think this program might not fail in n equals Fourier-Mills theory, when it almost surely would make no sense in a theory like QCD.
Okay, thank you so much, Mark. That was nice. Thank you.
So if there's no further questions, maybe I hand it back to Jan. Want to close things up?
Yeah, sure. Well, thank you very much, Mark, for that very nice talk. Thank you, everyone, for a very nice beginning of a very long 14-day journey, which we are going to embark upon.